Welcome back to the seventh video about capacitive liquid level sensing. In the previous video, we managed to actually measure the capacitance of our sensor and therefore the liquid level to a satisfying degree by just using an MCU and a single resistor. And yeah, the result was quite okay. And we could have left it by that, but then I mentioned, okay, what happens if your liquid changes its epsilon R and therefore the capacitance of your sensor changes? Card here, link in the description. In this video, we will try to solve this problem. Enjoy! We already talked how the relative permittivity, or also known as a dielectric constant, epsilon R, of the liquid in our container influences the capacitance of our sensor. If you don't remember, just rewatch part 1, card here, link in the description. And last time we got that nice curve here, the red curve. These were our capacitance measurements over the fill level of our container. And the black line here is just a linear approximation of that curve with the least square error. However, at the end, I filled up our container with some stuff from the sink, and suddenly we were measuring a higher capacity. So what happened there? We calibrated our whole setup for a certain epsilon R, let's say X. That was the epsilon R, or dielectric constant of water, so 80 or 78, whoever you want to believe. And then we filled in something with a higher epsilon R, an epsilon R greater than X. And in that case, we expect with the fill level increasing in our container, the capacitance of our sensor increasing faster than with just water. Likewise, if the dielectric constant of our medium is smaller than X, then we expect the capacitance of our sensor to increase slower as we fill up the container compared to just pure water. Now, directly measuring the dielectric constant of our liquid is basically out of the question. If you remember, our sensor and the electric field around it, it's complicated. Yeah, we have in red here our two copper plates wrapped around a wooden broomstick, probably pine, which has its own dielectric constant, and then we are wrapping that into an isolation made of some plastic which has its own dielectric constant, and then the electric field lines are going everywhere, crossing different materials with different dielectric constants. So yeah, that ain't working. The solution to that problem is to use a second sensor, a reference sensor, that just measures the change from air to liquid in the capacitance of that reference sensor, independent from the fill level of our container. The thing is, that's the theory. The technical implementation is quite far away from the ideal, as we will see. Here's my rather lackluster implementation of such a reference sensor. That's a combined sensor plus reference sensor. And as you can see, we have now 3 wires coming out at the end. So what's basically unchanged is that we have at the back that large strip of copper, which is our ground. At the bottom end of our sensor, I shortened one of the copper plates. This will be our sensing plate, which we will use to sense the liquid level. And in the free area, I added a small plate here, which is also, of course, isolated from our ground plate and our main plate. And this will be our reference plate, and that's that third lead that comes up here. And I intentionally routed that lead over the ground plate so it won't interfere with our main measuring surface here. A little bit more abstract, the whole thing looks now something like that from the side. We have here our ground strip, and then we have here our measurement, let's call it a signal strip, and then very short here at the bottom our reference strip. And right out of the box with that kind of sensor constructions, I spot a measurement error. Of course, the reference strip will not only interact as a capacitor with the ground strip, but it will also interact in some way with our signal strip and vice versa. Meaning our capacity signal that we will be measuring is signal to ground, the capacity signal to ground, plus the capacity signal to reference. The problem here will be what shall we do with the reference to minimize that? Should we also ground it? Then it's at least defined, or should we leave it dangle, high impedance? We'll see. The other way around is of course also true. So C reference is of course the reference to ground capacity plus also the reference to signal capacity. And that is of course the same. Assuming we don't do some magic here with setting some of these plates to high impedance or charging them to 5 volts or whatever. We will have to experiment a little bit with that. Before we go ahead and actually do some measurements in the container with some new code, which we'll also review, let's do some sanity checks regarding the capacity. And you noticed I also shortened, we will see that in a second why, my leads considerably. This should also minimize errors. But anyway, let's say here blue or pink is ground, and then we connect our signal plate and we get 11 picofarads. And now that's only 11 picofarads. Before it was 50-ish picofarads. So that was all capacity of the 2 leads wriggling around each other, which we eliminated. So that's good. Now as a test, if I also ground my reference plate, will that change something? Oh, it does change something. Then we have 14 picofarads. Oh. Okay, now let's try our reference plate against the ground plate. So that's also, that's also 13 picofarad. That's astounding. I would have bet that the capacity is lower. However, 14, yeah, it is lower, but yeah, it's 1 picofarad lower, one least significant digit. And now it's even higher. Come on, go down. 14, 13, 30. It was initially recorded with 13. Let's stay with 13 just so I don't go completely bonkers. And now let's earth our other plate and we go up to, let's say, 15, 16. You see, things might get complicated. Now to summarize, and I corrected the reading we got on the multimeter by the 2 picofarads we got as a 0 value. So C sig is 9 picofarads with reference floating, and C sig is 12 picofarads with the reference connected to ground. C ref, and we were astounded that it's so high. I explain why that is in a second. Is 11 picofarads with sig floating, and it's 13 picofarads with sig grounded. The reason for these comparably high capacity values is our lead here. And that is, yeah, routed very closely to ground. Maybe that was a mistake. And though the distance between ground and these, 10, 12 centimeters of lead is very close, meaning that produces a large amount of capacity. Yeah, remember, capacity is inversely proportional to the distance. The smaller the distance, the higher the capacity. And here's a new hardware setup. I made a Lego compatible breadboard for my little Arduino. Maybe I should do a Kickstarter for that, but yeah, probably not. Anyway, that's the reason we can now have these short leads that add very little capacitance to the capacitance of our sensor. The hardware setup for ground is still connected to ground, and it's the same for the now signal plate. And I have an additional resistor here, of course, for the reference plate. Here's the circuit diagram. We already know that part here from the previous videos. The only difference is now I labeled that capacitor here C sig for signal. That's the new part. We use a digital 17 via a resistor to discharge our reference plate or reference capacitor, and we monitor the voltage across that plate, that is that capacitor, using D18, which can be used as an analog input on an Arduino Nano Every. And I intentionally left D19 empty, so we have some separation between these two circuits to minimize interference. So let's go over the sketch real quick, which is really just an extension of the sketch from the previous video, but now supporting 2 sensors. So I still have here all my constants for my now signal sensor. So the sense pin, the drive pin, the charge time in microseconds, which is now 100, the resistor value in mega ohms, which is now 2. I'm using now 2 mega ohm resistors, less noise, yeah. And the discharge time in milliseconds. And I have exactly the same set of constants here, so duplicated for the second sensor, the reference sensor. And here the only difference is the charge time is 150 microseconds. And at some point I will talk about how to fine-tune these constants. We still have our average and measurements parameter, which I increased to 20, so less noise in the readout. And now we can continue with the setup. In the setup, I still initialize my serial interface and I still set the pin mode for our signal sensor to output and set it to low. But now little enhancement here, then I do a delay with a discharge time just to make sure it's really discharged before I go into the main loop. And I duplicate that for the reference sensor. And now we go bottom up like last time. So I have here all the math encapsulated in the unchanged function capacitance in picofarads. We don't have to talk about that again. The function measure capacitance in picofarads doesn't rely on global variables or doesn't access the global constants anymore. Instead, it gets here a set of parameters, and that is the sense pin, the drive pin, the charge time in microseconds, the resistor value in mega ohms, and the discharge time in milliseconds. Otherwise, it's almost unchanged. Just a few improvements here. I no longer wait here after I set my drive pin to low for the discharge time. I'm assuming now, and the program logic has been adapted accordingly, that we are discharged. I'm still reading the voltage at the discharge point, and I still have here a sanity check, an error, print out if the discharge value is now greater than 1% of my full scale. No longer 10%, just 1%. I found out that it's really just a few least significant bits noise we have here when we're discharged. Nothing to write home about or to worry about. The rest is absolutely unchanged. But for the fact that I do my delayed discharge time now at the end of the measurement when I switched my drive pin to low. So making sure after I go out of my measurement function that my sensor is discharged. And that brings us to the loop where I now have two float variables for storing capacitance. One for the reference sensor and one for the signal sensor. And both are initialized to 0. And then I do my n measurements twice this time, each time in the loop. One for the reference capacitance here and one for the signal capacitance. The structure is the same like last time, just handling two sensors. Then I divide my values through the number of measurements, getting the average value, and then I print them out. And that's it. And that's how the whole thing looks on the serial monitor. Now we have two values, the reference capacity and the signal capacity. And this time, to get a little bit more data, I will fill the container in 25 milliliter increments, and I won't film that all because, you've seen it before. So I will come back to you with the results, so the usual Excel graph. And here are the numbers. So blue is our signal and red is our reference. And right off the bat, we noticed that we are measuring here in air for the signal 30 picofarads and 40 something picofarads for our reference sensor. And with a multimeter, we measured something like 12 picofarads and 13 picofarads. There are two possibilities here. First, our Arduino is not measuring as exact as we thought. I mean, we got the impression in the previous video that it really measures capacity quite accurately. The second is, of course, we connected now the breadboard, which it itself introduces, together with the inputs of the Arduino, additional capacitance. Your choice. Or I have a bug in my software. Always a possibility. But in itself, the measurements are consistent. So let's run with that. Of course, our reference sensor makes a jump here, and then it almost, and that's a problem we have to talk about, plateaued out. Of course, it's only covering here at the bottom about, I measured it, 11 millimeters. So this is air, and this here is 11 millimeters if we sensor height. So 11 millimeters. Can you still read that? Probably not. Doesn't matter. We will have another look at the numbers. And then ideally, it should plateau out here. So we got here a delta for 11 millimeters of about 5.5 picofarads. And then we have this creep here, where it's slowly but steadily increasing. Not as hard as, not as steep as for the first 11 millimeters, but it's creeping, and that's a no-go. That's a no-go. We have to get rid of that. The creep can be caused by, we talked about that, this error source here. So my reference plate is interacting with the signal plate, which is connected to ground via a 2 mega ohm resistor when in the discharged state. And as the fluid level, I mean, we are here inside in the broomstick, but here on the outside where the liquid is, the capacity increases when the water level increases. However, I think this is only a very small error. Because you see, the creep is quite constant over the whole range from 100 milliliters down here to 600 milliliters. Meaning that creep must be caused by something else. And I guess the most likely culprit here is my lead running up here from my reference plate along, or better say on top of my ground plate. You see my ground plate here in blue and my lead from the reference plate here in, the little green dot. The field lines between them, they pass a lot through the outside, that is through the liquid, and that means as the liquid level rises, the capacitance of that lead rises, and so we get some creep. At least that's my theory for the moment. The blue signal line, of course, starts increasing now only when we reach the 100 milliliter mark, because our main sensor now, it starts at about 100 milliliters. And from there it's almost linear. So that's very good, but that's what we expected. But now, how can we calculate the fluid content of our container or the fill level of our container from just these measurements here and the reference sensor without really calibrating using data from all along that blue signal line? We know that our reference sensor changed its capacity by 5.5 picofarads within 11 millimeters, completely covered by the liquid. And we're ignoring for now the creep we got afterwards. So we have here a capacitance per height calculated as the capacitance change of the reference, our 5 picofarads, divided by the height of our reference sensor here, which is 11 millimeters, and that gives us a change of 0.5 picofarads per millimeter with liquid covered in our sensor. Our signal sensor started out with a capacitance of 30.5 picofarads in air, so that's the blue baseline here. If we now just consider the change in capacitance here as the liquid level rises, and we divide that change by the capacitance per height, which we derived from our reference sensor, then we get here the capacitance of our signal sensor at some level minus the capacitance of our signal sensor in air divided by those 0.5 picofarads per millimeter, and this gives us the signal height, hopefully. So how high the liquid level was across our signal sensor. Now we know that our container has a certain volume per height. It's not quite linear, but close enough. And if I just measure between the 600 and 100 millimeter mark, so 500 millimeters, that comes out to about 84 millimeters. So our volume per height for our container is 500 millimeters divided by 84 millimeters, and that gives us about 5.95 milliliter per millimeter fill level. We also know that our signal sensor starts at about, if I guesstimate it, 100 milliliters. So we have here a signal offset of 100 milliliters. So if we multiply our signal height with the volume per height and add our signal offset here of 100 milliliters, we should get the volume of liquid in our container, hopefully. Please note that this of course assumes that the geometry of your signal sensor and your reference sensor is identical, but for the height. Here's what you get when you put that math into an Excel spreadsheet. So green is our actual level in milliliters inside our container, which is of course a perfect straight line. So 100 milliliters are 100 milliliters, 200 milliliters are 200 milliliters, etc. The blue line measured is applied the math to the capacitance we measured across our reference sensor and signal sensor, and this is, but for the region below 100 millimeters, quite close to the actual fill level of our container. Of course, we can't get sensible data below 100 milliliters because our signal sensor starts above 100 milliliters. That's a drawback of that special topology here with the signal and the reference sensor. Of course, you could build something if you had the space where the reference sensor is in parallel to the signal sensor. Anyway, Red is the difference between the two curves, and that scale applies here between minus 20 milliliters and 100 milliliters. And if we just ignore everything below 100 milliliters, then you see the error we get is below plus minus 20 milliliters. That's quite good. Note that the only capacitance measurements we took for calibration were the air capacitance of our signal sensor and the air capacitance of our reference sensor. Everything else were just geometry measurements here. What's the height basically, and the relationship between height here in our container and the volume. So whatever the dielectric constant of our liquid is, we should always get a proper volume, respectively height measurement. That's good, but for the fact that we have that creep here, and we really need to get rid of it. We already have a theory about what's causing that creep. That is our reference lead here outside. So we need to really shield that reference lead here by putting it into the inside. Then we will probably have some interaction here with the signal plate, so there would be some field lines along here. However, we'll have to see how great that effect is, because the distance will be quite large, and we'll have just to run with it and see the effect. So we're going to build a sensor version 3. Here is sensor version 3, not quite finished, but I wanted to show you some details. So we still have here at the very bottom our reference plate, and then I milled a groove here in which I embedded the cable, the lead for the reference plate. I wanted to show you that before I put the ground plate on top of that. And then, of course, here in the upper part we have our signal plate. Here's the almost finished sensor version 3 with the lead to the yellow lead to the reference plate buried under the ground plate. Unfortunately, the glue here at the end that I used to seal up has to dry. And that means we are out of time for today. This takes a while, and yeah, it's already late. Anyway, next time we will finish up with our reference plate, reference sensor thingy, hopefully, and yeah, get perfect results this time. Or maybe this time. We'll see. Anyway, till then, bye.